In this video, we will take a look at the basic properties of tangents to circles. First of all, let's take a look at the meaning of tangents. When we have a circle and a straight line, there are only three cases. They can have 2 points of intersection, 1 point of intersection, or no point of intersection. In this section, we will take a look at this case, the case of 1 point of intersection. In this case, this straight line is known as the tangent to the circle. A tangent means a straight line which intersects or touches the circle at only 1 point. And this point of intersection is also called the point of contact. Now we know that a tangent means a straight line which intersects the circle at 1 point only. But please be careful. In this case, this straight line is not a tangent to this circle, because when this line is extended, it will intersect at 2 points. Now let's take a look at the basic properties of tangents. Suppose the point of contact is P, then when we join P to the center O, these two lines OP and AB are always perpendicular to each other, and this property is known as tangent perpendicular to radius. Now let's take a look at the proof of this property. Here AB is the tangent to the circle at P and O is the center of this circle. We need to prove that angle OPB is a right angle. To do so, first of all, we may assume that angle OPB is not 90 degrees. Based on this assumption, we can construct a perpendicular line like this. If we consider this right-angled triangle OPQ, then we can conclude that OP is longer than OQ because OP is the hypotenuse of this right-angled triangle. However, if we consider this point N on the circumference, then we can conclude that OP is equal to ON because they are the radii of this circle. Therefore, under this consideration, we should conclude that OQ is longer than OP. But there is a contradiction because OP cannot be longer than OQ and at the same time OQ is longer than OP. Therefore, we can conclude that the assumption is wrong and therefore angle OPB must be 90 degrees. That's why the tangent is always perpendicular to the radius. Actually, the converse of this property is also true. That means if we are given a figure like this, and we are given that angle OPB is 90 degrees, we can actually conclude that this line PB or APB is the tangent to this circle at point P. And this property is known as the converse of tangent perpendicular to radius. Later on, we can apply this theorem to show that a straight line is a tangent to a circle. Now let's take a look at the proof of this theorem. Here O is the center of this circle and angle OPB is given to be 90 degrees. We need to prove that AB is the tangent to this circle at P. Again, first of all, we may assume that AB is not the tangent at P, and that means AB should intersect the circle at 2 points, and we may call the other point Q. Because OP and OQ are the radii of this circle, they should be equal. That means triangle OPQ is isosceles and therefore angle OPQ should be equal to angle OQP. That means these two angles should be 90 degrees. On the other hand, by considering the angle sum of triangle, we can conclude that the angle at center is actually equal to 0 degree. But if Q and P are two distinct points, angle O should not be 0 degree and therefore there is a contradiction, and that means AB has to be the tangent to this circle at P. That's why when we are given a right angle like this line AB is always the tangent to this circle, and this is the converse of tangent perpendicular to radius. To conclude, in this video, we have learned two basic properties of tangents to circles. The first one is tangent perpendicular to radius, and the second one is the converse of the first one. That's the converse of tangent perpendicular to radius.